Welcome to G Fun Facts Online. Today, we are going to dismantle one of the most persistent illusions in the history of astrophysics. We are talking about the death of stars. Specifically, we are talking about the geometry of the apocalypse. For a very long time, if you opened a textbook on stellar physics, you would see diagrams of supernovae that looked pleasingly perfect. A massive star runs out of fuel, collapses, and then bounces back in a beautiful, uniform sphere. It was a neat, symmetrical mathematical solution, but it was also wrong. Recent breakthroughs in 3D computer modeling and high-fidelity observations from the James Webb Space Telescope and the Chandra X-ray Observatory have shattered this spherical illusion. We now know that when a massive star dies, it does not expand as a ball. It expands as a lopsided, turbulent, and complex structure that astronomers are calling the Clam-Shell Geometry. This is a story about how the universe breaks symmetry to create complexity, and why the chaos of a clamshell explosion is actually the reason we exist. To understand why this new geometry is so revolutionary, we have to look back at why we got it wrong in the first place. For much of the 20th century, the standard model of a core collapse supernova was the spherical cow. In physics, a spherical cow is a metaphor for highly simplified models of reality. In the early days of computational astrophysics, back in the 1970s and 80s, computers simply did not have the processing power to simulate 3 dimensions. To make the math solvable, physicists assumed spherical symmetry. This effectively turned the star into a one-dimensional problem. You only needed to calculate what was happening along a single line from the center to the surface, and then you could assume it was the same in every other direction, effectively rotating that line to make a sphere. In this one-dimensional world, the mechanism seems simple. The iron core of a massive star, something more than 8 or 10 times the mass of the Sun, runs out of fuel. Gravity wins. The core collapses at 25% the speed of light. It hits nuclear density, becomes a proto-neutron star, and the infalling matter slams into this hard surface and bounces off, creating a shock wave that blows the star apart. It sounds plausible, but there was a massive problem. When theorists ran these one-dimensional simulations, the stars refused to explode. The shock wave, battling against the immense gravity of the infalling matter, would stall within milliseconds. It would run out of energy and die, creating a fizzle instead of a bang, and the star would simply collapse into a black hole. The spherical model predicted that supernovae should NT exist. Yet, we see them everywhere. This was the crisis of the spherical model. It turned out that the spark that revived the stalled shockwave wasn't just more energy, it was entropy. It was asymmetry. The universe needed to break the sphere to make the star explode. This brings us to the modern understanding, the Clam-Shell Geometry. This isn't just a random shape. It is a specific morphology defined by bipolar lobes and broken rims. Imagine a clamshell prying open. You have the hinge, which is the central neutron star or black hole, and you have the shells, which are 2 massive lobes of ejecta, blasting out in opposite directions. Sometimes it is unipolar, meaning a single dominant lobe takes the majority of the matter, leaving the other side relatively empty. This geometry creates 3 distinct structural features that we can actually observe. First, we have the toroidal atmosphere. In a rotating star, the infalling matter swirls, creating a donut shape or torus of dense material around the equator. When the explosion happens, the blast wave struggles to push through this thick equatorial donut. It takes the path of least resistance, which is out through the poles. This funnels the energy upward and downward, creating those 2 expanding lobes. Second, we have the broken rim. In remnants like Cassiopeia A, we don't see a continuous bubble. We see large gaps, where the explosion was weak, and bright knots where it was powerful. These are the fingerprints of turbulent bubbles of hot gas that boiled up from the core, breaking through the star's surface in patches rather than a uniform sheet. The third, and perhaps most telling sign, is the displaced heart. If a supernova were a perfect sphere, the neutron star left behind would sit dead center, motionless. But we observe neutron stars racing through the galaxy at speeds of over 1,000 kilometers per second. That is over 2 million miles per hour. This is Newton's third law playing out on a galactic scale. For the neutron star to be kicked that hard in one direction, the explosion must have been significantly stronger in the opposite direction. The explosion was essentially a gunshot, shooting the ejecta one way and the neutron star the other. But what drives this asymmetry? How does a round star produce a lopsided explosion? We now believe it comes down to three hellish mechanisms occurring in the first few seconds of the collapse. The first is neutrino-driven convection. When the core collapses, it releases a flood of neutrinos that carry away 99% of the energy. These neutrinos heat the material just behind the stalled shockwave. Think of a pot of thick oatmeal boiling on a stove. The heat comes from the bottom. The oatmeal begins to bubble and convect. In a star, these bubbles are mushroom clouds, thousands of kilometers wide. As these massive bubbles rise, they push the shockwave outward in specific spots, deforming the sphere. The second mechanism, and currently the leading theory for the clamshell shape, is the standing accretion shock instability, or SASI. Imagine the shockwave as a spherical dam holding back a river of infalling gas. As the gas hits the shock, it doesn't just sit there. It starts to slosh back and forth, like water in a bathtub being carried by shaky hands. This sloshing grows more violent over time. The shock wave creates a spiral mode, physically deforming the explosion into a figure 8 or hourglass shape. Eventually, the explosion finds a weak point and bursts through, creating a dominant axis. This sloshing naturally sculpts the clamshell out of the chaos. The third mechanism involves jittering jets. In stars that are rotating rapidly, an accretion disk forms around the new neutron star, firing jets of material outward. But because the environment is so turbulent, the jets don't point in a straight line. They jitter. They act like a power drill, wobbling and carving out large cavities in the star's interior, pushing matter into the dense walls of the shell. We aren't just guessing this happens. We have smoking guns in the sky. Let's look at Cassiopeia A, the poster child for supernova asymmetry. Located 11,000 light-years away, recent images from the James Webb Space Telescope have revealed that Cass A consists of a main shell that is heavily fragmented. Astronomers have identified two distinct jets of high-velocity material shooting out to the northeast and southwest at 15,000 kilometers per second, much faster than the rest of the shell. Even more incredibly, in 2024, Webb revealed a structure nicknamed the Green Monster, a loop of gas in the interior that is likely the result of the SASI sloshing mechanism pushing a wall of debris into the surrounding material. Then there is Supernova 1987A, the closest supernova of the modern era. It is surrounded by three rings forming an hourglass shape, which is essentially the projection of a bipolar clamshell. For 37 years, the neutron star at its center was missing. Just recently, we found evidence of it, and the reason it was hidden is likely because it was obscured by a dense, asymmetrical dust blob, further proof of a lopsided explosion. And we have seen this happen in real time. In 2024, astronomers studied a supernova called SN 2024 GGI using spectropolarimetry, which measures the direction of light waves. They mapped the shape of the explosion just hours after it happened, and the result was clear. It wasn't round, it was olive-shaped. This confirmed that the asymmetry is born in the very first second of death. So why does this matter to you? Why should we care if a star explodes like a ball or a clam? because this geometry is fundamental to our existence. First, there is the origin of elements. We are made of star stuff. Calcium in our bones, iron in our blood. In a spherical explosion, elements would be layered like an onion, with iron trapped in the middle. In a clamshell explosion, the turbulence dredges up the iron from the core and sprays it out past the oxygen. This mixing is crucial. Without this violent asymmetry, the heavy elements might fall back into the black hole, and the universe would be a much simpler, emptier place. Second, this sloshing emits gravitational waves. A perfect sphere does not ripple spacetime. A lopsided, sloshing explosion does. Next-generation detectors are being designed to listen for this specific hum, which would let us hear the heartbeat of a dying star. And finally, the kick of the neutron star spreads these exotic objects across the galaxy, seeding different regions with pulsars and magnetars. The clamshell geometry teaches us that perfection is not the default state of nature. The death of a star is a violent struggle between gravity and entropy. The broken rims, the bipolar jets, and the off-center hearts of these remnants are the scars of that battle. It turns out that to build a universe filled with complex chemistry and life, you cannot rely on the perfection of spheres. You need the chaos of the clamshell. As our telescopes grow sharper, we are finding that this asymmetry is the rule, not the exception, revealing a cosmos that is dynamic, lopsided, and spectacularly alive. Thanks for listening to G Fun Facts Online. We will see you in the next deep dive.